So hello everybody. In this section, we are going to talk about this question, which is the 31st problem in Project Euler. So hello, let's see the question now. Okay, here, coin sums. In England, the currency is made up of pound and pence. Basically, pence is equivalent to 100 pounds, which is stated here, and there are 8 coins in general circulation: £1, £2, £5, £10. No, 1 pence, 2 pence, 5 pence, 10, 20, 50, £1, and £2. So it's possible to make a £2 in the following way. So you will get this combination. This is the sample combination. So you might get other combinations other than this. So there are many combinations as the money goes bigger. Let's say for 5, you can have 1 plus 2 plus 2. You can have 1 plus 1 plus 1 plus 2. There are 2 combinations here. So another combinations would be 5 alone. So how many different ways can a £2 be made using any number of coins? So now I'm going to talk about the first method, which is depth first search. Okay, the code is as follows. So basically, what I do is, perhaps I use a picture to illustrate how I do it. So this is 200. It's a bit small, so we make it bigger. Okay. 48. Okay. Right. Next, let's see what type of coins that we have. Okay. So what we can make from here is we take a coin away. So since 200 can take all of the coins and is still valid, because something like if you have 100, you can't take 200 because your money is simply not enough. So for 200, you can take all of the coins. So your money will be like this. If I take 2, then it will be 198. If I take 5, then it will be 195 and 190, and this one is 0. This is 150, 100, and this is 0. So at this moment, we can see the tree is being formed like this. Okay. So yes, this is something like this. So at here, you can do the same thing over again, but for this time you cannot take 200 because the money is not enough. So you do the same thing again, and for here you do the same thing again, and for here you do the same thing again. Okay, so until you reach 0, then that will be one of the combination. After that, you get the total number of combination. But the problem is that you might encounter the same combinations again by using this method. So you need to put some filter, because let's say if you take 5, right? Let's clear this. Okay, if you take 5, then you can take away 1, and you can take away 2, and you can take away 5. The word in the bracket stands for the coin that we took. So at this moment, we can take 1 away and 2 away. And for here, we left 2, so we can take 1 away, which remains, which has 1 as remainder, and we can take 2 away. So what? Sorry, we can take 2. Okay, we can take 1 away. So left 1, and we can take 2 away, which left 0, which this will form a combination for 5. So there's nothing left. So okay, this should be 0. Okay, for here, we can take the thing again, take away the money again. So if we take 1, then what we will get, we will, if we take 2, then we left 1. And here, 2, 2, then we can take 2, and take 1 away, then we left 1, and we can take 2 away, which we will get 0. Okay, let's draw a line to prevent confusion. Okay. So from here, we can take 1 away, 2, 1. So some mistake here. This should be 3, because I took 2 away. Okay. So this should be 2. Okay. So we left 2 here because we took 1 away, and we left 1 here because we took 2 away. Okay. So well, here we can take 1 and 1 or 2 because we left 2. So 1 or 0 because we took 2 away. So the tree is pretty large, even for 5. So as you can imagine, if the number is big, that so this method would not work well. So I have another method by using dynamic programming, which I will explain later. So just be patient for this method, BFS. Okay, for here we can take 1 away. So what we left is okay. At this point, we still have this. Okay, seems like the space not enough. Let's move here to a larger space. Okay. Here. So we still can expand something here. We take one away and we take two away, so we should 0. And for this we take one away because the remaining only is 1, and here we take one away. 0, 1. 0, 1, 2. So again we take one away, so the remaining. Okay, finally the tree has been finished. Okay, so what's the combination here? 1, 1, 1, 1, 1, and 1, 1, 2, 1, and 1, 2, 2, 1. Sorry, 1, 2, 1, 1, and 1, 2, 1, 1. As you can see from here, the combination duplicates. Oops. These combinations and this combination because sequence is not important in this case, so this the answer from both branches are actually the same solution. So yes, as you can see from here, there are 3 1s and 1 2. So you need to take account into this solution. But I did something like this by cutting the branch. So let's say if for the last line that we took the coin away, we don't have to take the coin that is bigger than the coin that we took away. So basically, I will take the coin according to from large to small. So in the end, how's my tree looking? So okay, let's remove this all. If I take 2, then I won't take 5 again, or the number larger than 2. So by this method, then I can eliminate the identical solutions, and this reduces the recursion effectively. Okay, this is wrong. 3, 2. So we took 2 away, and this we. So by this method, right? Since we took 1 away earlier, so I only take 1, and anything which is more than 1, I will not take. And as these cases will be taken by the number larger than 1. So 2, 1, and 1, 1, and 0, 1. For 2, you took 2 away earlier, so you can take 2 again, or you can take 1. The remaining money is 1, so we can only take 1. So the remaining money is 2. So we took 2 earlier, so we only can take 1. We took 1 earlier, so we only can take 1. So this will be 0, 1. So by this method, our solutions are as follow: 2, 2, 1, as from, as you can see from here, or 2, 1, 1, 1, or 2, 1, 1, 1, or 5. So by using this method, you can eliminate the need to store the solution that you have found, which is pretty elegant here. So by using this method, the solution that you found will be, you will get the solution according to the biggest coin, from the biggest coin to the smallest coins. As you can see from here, we get 2, 2, 1, and cases like 1, 2, 1, 1, which is similar to this, which is actually, in fact, this that is completely the same with this solution, will not be formed. Okay, so let's see the code. So initially, I just open a BFS function. So if sum equals to 0, 0 equals to, if sum equals to 0, which means that if our sum, the money that we have is 0, then we'll return 1. That is one solution. And next, count. Count is the number of solutions that we have found. So for coin type, length equals to 1, which is declared here, which is the number of coins that we have, the type of coin that we have. We look through it, and if we found that the number is smaller or equal to the coin type that we have, which is something that in last recursion we put 2. So for the next recursion, we won't touch 5, 10, or we only touch 2 or 1. So we only take 1 or 2 to realize that the algorithm that I discussed just now. And the sum is more than coin type, which means that we have the money, and the coin type that we take is less than or equals to the money that we have. So this is basically the same with the algorithm just now, but this is in code. So count, so we just add, we do a DFS add, go to the bottom and get the solution and go up again. So it will be like this: 5, go down, and should be start with 5 for my algorithm. So if we go to 5 and we go to 2, return, and go to here, return, and go to here, and return. So yeah, this is it about this question. And since the question requires 200 pounds to be separated, we need to find a way of combinations from the coins that we have to form 200 pounds. So I just put 200 pounds here and last put. So you should change if your value at here is different. So for 200, I just put 200 because it's just right with the coin types that we have. So it will look through 200, 100, and so on. So let's run and yes, we got the answer, which is 73,688. 82. So yes, this is the same answer with official answer. So yes, this, and okay, so let's take a look at this, the dynamic programming solutions. This is even simpler. Okay, so this is the code, and usually we start an array to solve number of ways that we can form 200 pence of £2. So in fact, by using this method, you get very high performance, because it basically store the solution that you have found earlier. So let's say for 2, because you have found here, so and eventually will goes into this again, and the combinations can be formed by 2 is the same for all cases. So this loop does that operation. So let's say for 1, so basically we'll construct it like this. Oops. For 1, 2, 3, 4, 5, 6, and so on. So if we put 1 pence into 1, then we will get 1 metal, 1, 1, 1, 1, 1. And if we put 2, and the remaining is 0 here, so we can't put it anymore. Then if we put 2, then this is 2, so we can add a combination, so it becomes 2, 2, 2, 2, 2, 2, and so on. So in fact, 3 can be constructed by adding the combinations from here to here, because 1 plus 2 equals to 3, and 4 by 3 plus 2, and so on. So this is a typical knapsack problem that you might have so far, or you might not see. So this is much faster, and you get the same solution. So if for big money, let's say perhaps 10,000, so this method will works very well. And if you try with the DFS that I have discussed just now, it will be very slow. So perhaps let's see the time taken. Okay. $10,000. Okay, as you can see, this is slow, so we'll use dynamic programming, which is here. This is 10,000. Okay. Okay, sorry. Okay. So as you can see, the processing speed is basically instant, it comes out. So this is a much faster way if you can imagine of. So in fact, the DFS is easy if you don't know about dynamic programming, but when the numbers goes bigger, you've got to settle down with dynamic programming. So yes, this is the end of the 31st problem in Project Euler, which is named as coin sums.